Hello, yeah, in this video, we'll continue to work on Poisson regression model using R. Just show you how to do some additional analysis for a fitted Poisson model. First, I just want to say, I want to make an acknowledgement. I have used some of the materials from these websites, so just want to acknowledge, these websites first. Okay, so first is to get a data set from the built-in package, our package data set, and then get a data set called warped breaks. Then we can fit a Poisson model. So this is the summary, and we can fit a QuasiPoisson model. And here's the summary. Okay. So before we start, let me emphasize that a Poisson regression model is a special case of the generalized linear models. So, and as we know, for GLMs, the parameter estimation is done by using maximum likelihood estimation. So we have the likelihood ratio test. We have the AIC value for all the generalized linear models. And so they're also available for Poisson regression model. Okay. Okay, so once you fit a Poisson regression model using R, you've got the regression coefficients. And if you worry about over dispersion, then you fit a QuasiPoisson regression model. I think the key is to kind of modify the variance function so to address the over dispersion issue. So we can compare Poisson versus a QuasiPoisson model because we just fit both models. First, let's load the library ARM because we need the se.coefficient function to get the standard errors of this regression coefficient estimates. So the coefficient 1, coefficient 2, SE1 and SE2, and we just put all these estimates together, and we print out the data frame here. So what I want to show you here is you can see the coefficient 1, coefficient 2. Those are the parameter estimates, and they're exactly the same. Okay, right? So it doesn't matter whether you're using a Poisson model or a QuasiPoisson model, the parameter estimate for the regression coefficients are exactly the same. Okay, but if you look at the standard error of coefficient 1 and standard error coefficient 2, they are different. In general, the standard error for coefficient 1 are smaller for the standard errors of coefficient 2. Okay, that's because when you have over dispersion, usually your variance estimate and therefore the standard error estimates tend to be smaller than their true values. Okay, so if you get a smaller standard errors, then you inflate type 1 error rate when you do hypothesis tests. Okay, so this really shows you what that really matters is get a good variance estimate, which will lead to a good standard deviation estimate and then good standard error estimate. Okay, so there's one way is to change the model, for example, the QuasiPoisson model, or you can have a negative binomial model. All these models are kind of expanding the variance function to make the variance larger than the mean, so that you have some way to handle the over dispersion issue. There's another way you can get a better variance estimate. It is called the sandwich estimate. Okay, so you can install the package called sandwich and then load it in. then you can have this function called the VCOV, variance covariance function, HC, because the Poisson model type equal to HCO. Okay, so you can get the covariance matrix, and then from that you get the diagonal elements, take square root, get standard error, and then you can put all these estimates and the robust standard errors, and then the p-values using the standard errors, and then confidence intervals, lower and upper limit, and then print it out. So you can see this, the estimate, those are the regression coefficients, they're still the same. Now this time you have a robust SE, which should be better estimate when there's over dispersion, and then the p-values, the lower and upper limit of the confidence intervals are all printed here. So if you have a concern about over dispersion, you can also use the robust estimator or the sandwich estimator to get a better estimate for the standard errors. Okay. Next is really the confidence intervals. You can use the profile likelihood. You can get the confidence intervals for the regression coefficient, and then you can convert them into confidence interval for the incidence rate ratio. And these are really good for making reports. Okay. And also you can have the type 3 analysis by using likelihood ratio test. It will test whether each individual predictor is significant or not. And this is useful when you have a categorical predictor with more than 2 categories. Okay. And also if you have a nested model, you can compare the 2 models using likelihood ratio test. So here I fit another model, Poisson model 2, by delete one of the predictor called Wu, right? So you can add a predictor or you can minus a predictor. So this Poisson model 2 will not have the Wu predictor. So model 2 was nested. It's nested with the model. So I compare the 2 models. This tells me the predictor Wu is highly significant. So that means it's worthwhile to put it in the model. Okay. And then there are some goodness of fit tests. First, from the residual deviance, you can use the residual deviance and its degree of freedom to conduct a goodness of fit test. So just testing if this model is actually worthwhile to fit at all. And then you can use the model predicted versus the observed counts, and then calculate a chi-square statistic, and so that's the Pearson statistic, and then you can use that. Also, its degree of freedom, you can compute a p-value for the Pearson goodness fit test. So for this model, both p-values from the goodness tests are very almost 0. So the model is highly significant there. Okay, so there's some different ways to check equidispersion assumption of the Poisson model. One is you can do some graphics. For example, you can get the predicted value for the lambda hat, and then you can plot out these 2 plots. One is the kind of the variance of the square of the residuals versus the lambda value, and look at the how wide the data spreading out. And also the Pearson residual versus the lambda hat. So from these 2 graphs, you notice some over dispersion. It's not unequal variance actually. So this would be give you some information about over dispersion. Another way to check over dispersion is to estimate the dispersion parameter, which is the Pearson statistic divided by the degree of freedom of the residual and which is called phi. And if this is much larger than 1, then there's over-dispersion concern. So for this model, it's 4.26. So there is a concern for over-dispersion. And you can also generate diagnostic plots, just similar to the multiple linear regression diagnostic plots. So here you get, so these are the plots for the Poisson model. You get both the residual plots versus the and also the impact statistics such as the Cook's D, the leverages, and things like that. So you can interpret these residual plots similar to the interpretations you use them for multiple linear regression, but just keep in mind here they're not as accurate as the plots in linear regression, because here we don't have continuous data. Okay, so just take observe the findings from these residual plots with a grain of salt. Okay. And the last one is you can make predictions from a fitted model. For example, if you want to have a new observation with U equal to B, tangent equal to M, you can predict the outcome. But the way to do that is you create a new data frame with the new predictor values, and then you just use the function predict with the model 2 and model 2, no, so I think it should be model 1, just model. Okay. Okay. So this new data equal new data type to the response, and this will give you a prediction. Okay. All right. Thank you for watching.